According to IEC 62305, buildings that are greater than 60 meters in height are vulnerable to side flashes or strikes below the top, but it only recommends protecting the top 20% no matter how tall they are. This fact exposes a flaw in the standard's core model, the rolling sphere method. Whether you trace its lineage to Edwin Whitehead's power grid studies of the 1960s and 70s, or to the work of Professor Tibor Horvat, which dictates that lightning simply strikes the nearest Earth object, the core flaw remains identical. Lightning does not strike the geometrically nearest object. Lightning strikes the object that launches the most aggressive, stable, upward connecting leader. And that's not something that can simply be determined with a ruler. Although it intends to define zones of protection, the RSM implies equal probability of a strike to the ground, the corner of a building, or the middle of the roof. In the case of very tall structures, the RSM would suggest an equal probability of a side flash of any current anywhere above the sphere radius, as well as some other odd implications when applied to atypical structures. Some RSM apologists argue that if the sphere is rolled such that its center moves at a constant speed, then the dwell time at any location gives a qualitative indication of probability. But that has no physical basis. And it would mean that there's no difference between a corner that's 30 meters high and one that's 300 meters high, or that there's no difference between the edge in the middle of the roof versus the periphery, which is obviously incorrect. Lightning distribution overwhelmingly clusters around the uppermost corners of tall structures. The RSM completely misses this reality because it treats lightning attachment like a simple geometric puzzle rather than a dynamic electric breakdown. Furthermore, IEC notes that many side strikes have low peak current values, something that cannot be explained by strict application of the RSM to buildings. However, using the electrogeometric model, the roots of the RSM as derived from Edwin Whitehead's research, it can be understood how strikes below the top could indeed be dependent on current. But this creates a paradox. The only strikes capable of bypassing the roof are so small that they lack the energy to cause any damage, so small that they fall below the design threshold of the rooftop protection system. But the fact that significant damage does occur, making the 20% rule necessary, indicates that high current strikes are bypassing the roof, and the RSM is completely blind to the mechanism allowing this to happen. Prior to a strike, or even if no strike occurs, tall structures are exposed to intense ambient electric fields generated by the buildup of charges in the clouds. These fields can trigger ion generation from exposed objects such as overhead ground wires, creating localized regions of shielding. If, just prior to the descent of a downward leader, such ions are generated, it could suppress the field at the ground wires. A lower portion of the structure launches the winning upward connecting leader. While current data for this specific event was unavailable, the physical scale of the upward leader indicates that this was not a low current event and likely involved space charge shielding. Similarly, tall buildings are exposed to intense pre-strike ambient electric fields which trigger ionization from protruding objects such as lightning rods, both sharp and blunt, and other objects on the roof that collect raindrops. Under intense electric fields, raindrops elongate and can act as sharp protrusions. This creates localized shielding, leaving other portions of the building to launch the winning upward connecting leader. This explains why damage is limited to the top portion of structures. Space charge shielding doesn't care about arbitrary percentages, it responds to electric field intensity, which drops off sharply as you move down a structure. The IEC's top 20% rule is just recognition of a reality that defies the geometry of the RSM. Some believe that the RSM is a conservative, safe model, but its poor risk discrimination and blindness to the physical mechanism causing high current bypasses proves otherwise. It's important to note that some systems which are highly prone to space charge shielding may not exhibit the same level of failure. Consider the protection system at NASA's LC-39B. Apparently designed using the RSM, it uses sharp-tipped rods and small-diameter conductors at a height of approximately 200 meters, which means it generates a lot of ions during storms. But given that the rods and wires are suspended on 30-meter-high insulating masts, generally the only viable competitors to launch an upward leader will be either a sharp rod in corona or a small-diameter conductor in corona. This means that both will be suppressed, but a preference for the rod with its lower leader onset will remain. More importantly, note that in some images of strikes to the system, the upward leaders exhibit an unusually tortuous path. They look more like upward flashes from very tall structures. Consider this image of an upward flash from the 553-meter-high CN Tower. The path of the Lightning leader is heavily influenced by huge amounts of ions generated prior to the strike. Given that the ions are the same polarity as the rising leader, they obstruct its path. But according to those monitoring NASA's system, there have been no upward flashes. This indicates that the system's upward connecting leaders and subsequently its lightning attractive radius are being suppressed by space charge shielding, but with little consequence. So far. Conversely, some structures which may be significantly lower than 60 meters may be highly prone to this effect, as well as suffer frequent damage, like church steeples. Here the geometry rather than the absolute height enhances the ambient field. The competition to launch the upward leader will be between a rod in corona and the structures immediately below the rod. Another critical factor is topography. Even a one-story structure located on a ledge or mountaintop could be prone to failures, because there's nothing magical about 60 meters. The issue is electric field enhancement. To fix the problem, one must go beyond simple geometry and employ electric field management, and that is the physics behind the Field-Sensitive Air Terminal, or FSAT. Unlike conventional rods that blindly ionize the air, the FSAT acts as a signal discriminator. It is engineered to suppress corona generation during the buildup of cloud charges, under both wet and dry conditions and regardless of any surface contamination. By resisting the formation of space charge, the FSAT remains fully exposed and instantaneously responsive to upward leader onset conditions. Crucially, adopting the FSAT requires no regulatory changes. The FSAT is a fully code-compliant Lightning mast designed to be used as a direct one-for-one replacement of standard sharp and blunt Lightning rods. It deploys at specific locations of high field intensity, such as building corners or spires. The FSAT addresses the problem of strikes below the top through high-voltage engineering. This allows designers to overcome the limitations of the rolling sphere method without changing their workflow.